Now let's go and use whatever we have learned about models for programming, or for computer science, or for information systems. So it means now we are ready to jump into the next part. What I will do now is I will show you that models are the basis for programming. Currently, models are mainly used for programming. In the future, models will be used as programs, but before we have to cope with modeling as programming. For this reason, I would like to say something about model-based development, modeling as programming, and I would like to base it on a number of case studies as well. We have covered a good number of topics already, 13 overall. We showed that modeling is an activity. We discussed methods for development. We discussed also methods for model utilization with all these different aspects. Now we will go to the future, modeling as programming. That is based on the model-based development initiative. We consider in this lecture modeling as programming, and for this reason we will show that models will become executable while being as precise and accurate as appropriate for the given problem case, while being explainable and understandable to developers and users within their tasks, their focus, their scope. Models will become changeable and adaptable at different layers, will become validatable and verifiable, and finally also maintainable. It means in this case we are not maintaining programs, but we are maintaining models and use compilers for the program development. As a reminder, a model is nothing else as an instrument that is adequate and dependable. Adequate means in this case it should be well defined or well structured, it should be analogous, it should be focused and purposeful. Dependable means it should be justified and sufficient, whereas justified means it should be cooperated, rationally coherent and conform, falsifiable, stable and plastic, and sufficient means it should have a firm quality and it should be evaluated. We already considered that a conceptual model is nothing else as a model that is enhanced by concepts from a conception space, of course formulated in a language that allows well-structured formulations, is based on mental models or perception models or domain situation models with all their embedded conceptions, and of course is oriented on a matrix that is commonly accepted. The matrix is a combination of the mold and of the deep model. The model itself is in any case a combination of the normal model, that is what we do normally, and of the deep model that is somehow inherited and of course reused in a number of cases, especially in our modeling case as well. Models are mainly, of course, model suites. They consist of a collection of well-associated models, and for this reason we should also cope with model suites in this lecture, but I will restrict the consideration to what has been already given in lecture 9. Okay, I claim now that models will become the next generation of programming, so that everybody can program. So we will have something like true 5th generation programming. With the 5th generation project, of course, we should come back in a minute. First of all, let us discuss what has been done so far. Traditional thinking is based on mental habits and disciplines for designing of useful software. Of course, it is somehow cultivated in our area. The skills of design and software crafting are somehow developed. That is some kind of new science, a long theory and experiment. That means in this case we have a specific means, and algorithms are the main tool the directions to control the computational model by an abstract machine to perform a task. To compare it with the new computational thinking, we have to somehow to accept that instead of mental habits and disciplines are used now problem formulation so that their solution can be expressed also as a computational step. Computational thinking is a conceptual framework that enables programming. We have sets of problems and sets of problem-solving concepts such as representation, divide and conquer, abstraction, information hiding, verification and logical reasoning that can be inherited as some kind of generic models. They are useful in science and most other fields, and algorithms are now becoming expressions for recipes for carrying out tasks. That means we do not need any more awareness of computational models. We directly inherit those. We can continue this line with some other observations about it. Traditional computational thinking, programs are tightly coupled with algorithms. Programs are algorithms expressed in a computer language. Algorithms derive their precision from a computational model. Now we have programs are loosely coupled with algorithms. Algorithms are for all kinds of information processes, including humans. It is completely optional whether an algorithm will ever be translated to a program. From the classical traditional thinking will be again designing computations in a domain requires extensive domain knowledge. The new way to understand the problem is somebody schooled in the principles of computational thinking can find computational solutions in any domain. Computational thinking in the classical form is somehow oriented on end users that can follow algorithms and get the results without any understanding of the mechanism. Now we have a much better way how people can use programs with new computational thinking. People engage in any step by step procedures, are performing algorithms, and are maybe perhaps unconsciously thinking computationally. Of course, end users can be engaged in computational tasks without awareness of what is computational thinking. Now we can say, okay, no, people are engaged in any task that could be performed computationally, and for this reason they have a completely different understanding of what happens. We can envision that this is somehow an extension of the 5th generation program. You see here ISO, who is one of the fathers of the 5th generation project. At that time, in the 80s, last century, we wanted to have a sophisticated, layered, computation case-oriented hardware based on artificial intelligence, fuzzy logics, and neural networks that somehow integrates classical programming languages and also visual programming and more humanized languages. And of course, it is also somehow based on a very sophisticated language like Prolog. The problem is, however, the project failed. It failed not only because Prolog was not sufficiently expressive, but maybe it was too early. It was too highly dependent on artificial intelligence technology. It did not achieve an integration of artificial intelligence and human-computer interface techniques. It was oriented on one programming paradigm and especially on mathematical logics. As already explained in the section on languages, mathematical logics is a very nice semiotical framework, but it is not the most universal one and not the one that most users are using as a logical framework. The 5th generation project was also routed to basic programming blocks, and it was oriented on one final solution instead of coherent reasoning of coherent variants of final solutions depending on the focus and the scope of the user. The project failed, but however, this project still remains in the air, and I claim that modeling as programming will be the continuation of that project and will lead to completely different programming technology. I should prove it now in this lecture. There are some reasons why we need a true fifth generation programming. Computer users and also programmers are becoming, everybody can do it. That means in this case we can say, okay, fine, computer engineering has now reached a level of being a science. It has not got its culture. The education has, of course, and hampers a little bit. It's mainly education for handicraft work, but programming can more and more performed by laymen, outsiders, casual users, known specialists, self-made programmers. That means in this case, if we somehow establish a program modeling as programming, then in this case modeling will become much more elaborated. And of course we have already glimpses and pieces to handle it. Apps, modern facilities are already developed, but the problem is current apps and modern facilities culture is a bit problematic. And from the other side, so far in our computer science area, users have not been the main concern for programmers. We have still an operator or administrator thinking. That is somehow the common sense in our area. And for this reason, evolution has not been the real issue of a programmer that wants to have a solution now, but not for the future. That means migration, integration and maintenance is still a real nightmare. However, half-life time of systems and software is far lower than the lifespan of software deployment. Think, for instance, my database management systems thinking in the 19th was that the database management system and the database system will remain, let's say, for 5, maybe 10 years. Nowadays we claim, especially due to Basel III programs and requirements, that databases should be maintained at least 25 years and should be somehow accessible over the full lifespan of a database. We have also a problematic issue. Also, documentation is widely taught in computer science lectures. It is still a luxury. Documentations are nowadays generated from code. That is a bit problematic because if the code has no inner documentation, it has not a thoughtful architecture. If the code is using even monster classes like we often observe in UML and Java applications, or let's say if the code is done only once and does not really support modification, then in this case documentation, let's say generated from code, is not the right way. However, we need to have documentations and proper documentations that can be understood by any user of the system. That means in this case we should use a way to express what has been programmed by models. Why we should turn to fifth generation programming? I claim that the success of the 4 generations of programming languages directly leads to fifth generation programming. My experimentation with programming started with first generation languages and is now mainly concerned with fourth generation languages. First generation languages were machine level languages. They have been used for programming first generation computers, maybe based on an instruction code. Drivers and interfaces from firmware and hardware devices have had to be integrated, and the programmer should of course know what is instruction programming style. Second generation programming, that was already an big advantage. We used in this case assembly languages that could be directly translated to machine languages of the first generation. So in this case we have been relying on the assembler as a translator of a second generation language program to a corresponding first generation program. Third generation programs continue this line by developing a compiler technology. Those compilers translated programs to assembly programs. That means to assembly languages. We have had a good trial of somehow getting third generation programming as a high level programming. For instance, we have had languages like Ada or languages like PL1 that could be considered as universal languages, expressing any kind of programming issues. Those languages have been based on the Algol line, especially Algol 68. The problem is, however, that third generation languages have not having success to be based on a singleton programming language, but on a number of paradigms. The problem, however, is with paradigms that these paradigms are somehow misleading. Currently we are considering that object orientation is the best programming paradigm we could ever get, but there's a very nice book about pitfalls of object-oriented programming, and in this book you find 82 pitfalls that are very severe, especially whenever you want to evolve those things. Other paradigms are parallel programming, unfortunately not ready yet for real wide use. Procedural languages are still there and widely used. Functional languages are still in academia and the use is not really wide at present. We have predicative languages that almost died. We have rule-based languages that could be a nice form. We have also communicative languages, and those languages are far easier to use. All these are third generation languages. We stepped later to fourth generation languages. Fourth generation languages declare what should be done, but assume that we can somehow generate how things are done. For this reason we can of course concentrate on a little bit better human language, on the human form of thinking, and also on human conceptualization. The classical example for fourth generation language is SQL, the structured query language used for database applications. It is widely used in commercial daily use nowadays. It is a language that is of course concentrated on database issues. It is, however, a declarative language, and as a domain specific language it is a fourth generation language. That means in this case we can say, okay, fine, we stepped already from first generation programming languages to fourth generation programming languages. Why not? We should not step to fifth generation programming languages. The situation so far is pretty nice. We have a number of trials that could be extended to modeling as programming instead of modeling for programming. Model-driven architectures in development is a special form. We will turn to it in a minute. Conceptual model programming is another form that is a pretty nice initiative. Models and runtime used some kind of runtime environment, and then we can analyze what is the reason for a problem. That, let's say, a program has some, let's say, pitfall or some problematic, not very nice form of performance. Universal applications is a industrial utilization of genericity. We have a number of applications that are pretty similar. Think about a banking application in one bank and in another bank. Of course, you can generalize what you have learned in the first bank and then apply a program or specialize the generalization of the programs of the first bank to the second bank. Another issue is domain-specific modeling. That means we are using what we have been already doing in the 80s and in the 70s last century. We use languages that are somehow commonly accepted in the application domain, and for this reason we are using the language of the engineers that are working in that application domain. We have also framework-driven modeling like Gera and Monticore. We have also pattern-based development, unfortunately not really implemented so far into our tools and our environments. We have also round-trip engineering, model programming, inverse modeling, meta language modeling and programming. We have also reference modeling, and as a last modern initiative we have also model forensics. That means we detect the model within the code itself. That means in this case a model is then a documentation of the code, and the model will be in this case a pretty nice starting point for an analysis why the code has maybe some severe problems, or how to improve the code in a proper form, or how to integrate the code into another code. Model-driven engineering, as promised, starts classically with some kind of computation-independent model suite. Then we translate based on, let's say, tenets, based on some kind of rules, the computation-independent model to a platform-independent model or model suite, which can be again translated using some kind of support by some kind of libraries, using some kind of control to platform-dependent model suites. In reality, however, we are using domain situation models and the application situation for expressing what is really necessary to be, let's say, the basis for the programs and for the models. That means in this case we are using a domain situation model, intentionally at least, and transform it to a computation-independent model suite. Another initiative is the conceptual model programming. Conceptual models are widely used, for instance, in the database area, or for business programming, for business process programming as well. And in this case we could say, okay, fine, let's make our conceptual models executable, so that we can handle it directly as programs in the databases and user interfaces, and use some kind of pretty nice database access and user interaction support. In this case we are using a compiler that allows us to generate the corresponding code. The compiler code is beyond the purview of conceptual model for programmers, and the application system development becomes entirely model driven. That is a very nice initiative handled mainly by our Spanish colleagues that allows at least to handle conceptual models as already conceptual programs, at least for databases and database applications. Model-based systems engineering goes a little bit beyond that, beyond the traditional document-centric approach, directly to systems engineering, not only to software systems engineering. It is the formalized application of modeling to support systems requirements, design, analysis, verification, validation activities, beginning in the conceptual design phase and continuing throughout development and later life cycle phases. That means in this case models are primary artifacts, at least for the systems. And in this case, we can use them in a proper form. There are a number of successful tries already, and it can be the basis for our modeling as programming approach. Okay, in this case, what should be done? Let's consider first the simple case, information systems development. Information systems development, of course, is based on database management systems with their data structure design and conceptualization. We can use, for instance, an advanced entity relationship modeling language. We can use queries and programs, maybe based on some kind of visualization of SQL as visual SQL. We can have functions, mainly generic functions, that allow us to handle the support, the constraints, maintenance, and the view facilities. Information systems are, of course, the kernel for modern information system, for modern information structures, infrastructures. Information systems have as a kernel database management systems and extensively use user interfaces that must be programmed somehow. Use representation by workflows. Think what we have been doing in chapter 2 of this course. And of course, have to have some handling facility for distribution. Additionally, we need something for embedding software into its engineering and infrastructure, and for harmonizing. That means in this case, information systems development, design, and engineering can already be based on such kind of approach, going from what we have learned in databases and in workflow systems, and in web information systems, and in distributed systems, towards proper software and its engineering. The same can be done, let's say, if we consider computational thinkings. Then in this case, we use mental models. Mental models for the general and reference representation, for verification finally. We have a theory of computations that could support the whole thinking style. We have, of course, also software engineering approaches. In our case study, we used as a case abstract state machine engineering. You have, of course, also something like systems and its engineerings, maybe based on some cognitive support, based, let's say, on stories that a user plays with the system. And in this case, we consider it already as a specific case to be, let's say, discussed in our section or chapter 2 of this lecture. If we go furthermore from what we have been learning about the general setting towards the software and its engineering, then in this case, of course, we have software creation and software management, designing software, let's say, based on some kind of abstract state machine approach, or the software development and especially the software development process management, or the software post-development issues. And of course, in this case, we need also something on verification and validation. And in this case, we have something like a software organization with, let's say, an organization of functional properties that could be based on formal methods and maybe allows us a verification of the software. And the third branch would be, in this case, the systems and its engineering. Engineering could be done like we do in classical engineering. You have a description. That is what is currently done by program or by programming. You have additionally a technical support that is done by tooling, by frameworks, by environments, by compilers. You have also some kind of technology integration that could be done in future, and modeling as programming must do it somehow. We have an organizational layer integration in the architecture of the entire system. Then in this case you have obligations for users and for components of the system. You have of course also an economical layer, when to stop, when to finish, what kind of quality you need really, and what kind of quality characteristics is superficial and should not be supported. And of course in this case we could also think about evolution. That means in this case engineering should go far beyond what is done so far in our approaches. In engineering we properly treat also errors. As already said, we have systemic errors. That is a problematic case, and for this reason it should be avoided completely. We have systematic errors that should be also avoided. We have stochastic errors, at least if we know the distribution or the distribution functions, we can handle those in a proper form. And in this case we have also some kind of error prevention and error prevention models. I claim that generators are already common sense. We did it for website modeling. This poster is a poster that we have been using to display our approach to website modeling and website generation in website applications. Generators, you have some kind of editor, and you have of course a language like SiteLang to express what should be really done in a website. Okay, so in this case we would have now an agenda. The starting point is that models are used as sketch or inspiration for programming. That models for programming. That is what is currently done. The next generation will be modeling to program. Modeling to program means in this case we are using models as a mediator, as a blueprint, and somehow apply these models for during the development of codes. That is what we currently do as, let's say, an art. Modeling as programming in the future will do a little bit more. It allows to derive the program directly from a model suite or the programs. And the source code of the program is the model suite. So it becomes, during translation, an executable program. The third generation, beyond this, let's say, technology of modeling as programming, will be models as a program. That will be the mature phase for the true fifth generation programming. In this case, models are directly considered to be programs, and programming is nothing else as modeling, and the rest is transformation. You remember the lesson we have had with first, second, third and fourth generation languages. All have been using compilers to translate what has been, let's say, programmed to a lower level so that it becomes executable. In this case, models as programs would mean nothing else as we use a model as a fifth generation program and translate it to a fourth or third generation program that can be again translated to a second and first generation program. Yeah, why we should believe in this agenda? Okay, with entity relationship approaches we have learned how it can be done for databases. We learned also how to handle those things for, let's say, website modeling with web information systems development and design. The experience we have gained in our area has already been collected in the handbook of conceptual modeling and in the model to model and modeling cookbook we analyzed modeling techniques in different disciplines, and we realized that models are one of the main instruments that scientists, engineers, people have learned to use, and they have also learned to somehow to realize solutions based on models. That means in this case we should believe in this agenda in a proper form. Of course, it requires a little bit more efforts. Remember what a model is containing. A model is containing, of course, some kind of deep underpinning, the intrinsic grounding. It is, of course, based on development and utilization methods. It is somehow dependent on the context. All this goes to the deep model and is not, in any case, reconsidered. For the normal model, we might have, let's say, changes in the partially extrinsic basis. We are considering our scenarios and specific utilization spectra. And in this case, a model is functioning in these scenarios as an instrument. This depends, of course, of the acceptance of the community of practice. And for this reason, a model is containing a number of issues, or supporting a number of issues in a proper form. That is what we have been developing. And you remember, you can use a model house environment as a model of the model notion. The model suites and aspects we have been handling already in chapter 9. For this reason, I will not come back to it in this lecture. I will rely on chapter 9 for this case. Okay, now let's go for technologies, techniques and methodologies, so that we can use models really as a basis for programming. That means modeling will become programming. Then we need, of course, theories and practices for tooling. Okay, let's look what we have there. Modeling as programming is based on a number of concepts. First of all, we can say, okay, fine, we have model application areas. They have a specific context, they have specific molds, and that depends really what we want to have there in our engineering approaches. You have implicit injections of the deep model, you have an automatic enhancement of the model. You can also use whatever you have learned with the deep model especially, or with parts and pieces of the normal model for prefetching and pre-processing of the model kinds with directives and pragmas and defaults. We should consider those things in a specific form. We know also how to adapt and somehow materialize a model. We know how to compile model suites, at least for some cases. I will show in the sequence here, in the sequel. And we can also use model suites for the representation of various viewpoints. These concepts are ready for usage in our modeling as programming technology. That means in this case we could envision a work agenda, development of a model suite description environment, so that all models, the entire description framework is somehow handleable. We can also use some kind of support for deep modeling, for normal modeling, for mental representation, for stereotypes, for pattern, whatever we need there. We can develop on that part a systematic support for a model suite design development with an extrinsic normal model that is based on an intrinsic hidden deep model with stereotypes and pattern, within the definition framework for the construction of initial normal models. And we might use also some kind of compiler development. I will base my thoughts on a very early project that was established in the 70s and somehow realized in the 80s last century, that allowed us to compile specific domain-specific languages to a general purpose language. It was some kind of a compiler-compiler approach, because it was based on a compiler that translated a modeling or a programming language to another programming language. And then the compiler translated a program in the domain-specific language to a program in the general purpose-oriented language. It was based on component-based compilation of building blocks, and I think we can use the same approach. And it was also based on handling attribute grammars for representation of higher layers in the syntax definition and for associating pieces with other pieces in, let's say, programs. We have a number of application cases. Information systems models, I think we can handle really properly, even nowadays. Horizontally and vertically layered models, according to our model suite environment, can be handled based already on our experience. Adaptable and evolving model will be a task of the future. Service line models will also be a task of the future. But anyway, we have some kind of work agenda for establishing modeling as programming in a proper form. I told you already that the orthogonal concern is engineering. Remember it. Whenever we are handling modeling as programming, we should do it in the engineering way. That means in such a way that we can generate whatever is generatable without handling in a specific form anything else. Okay, do we have such kind of environment towards modelware and maybe to next generation literate modeling? My proposal would be a pretty simple one. We should say, okay, fine, let's have some kind of model specification. It is based, of course, on some kind of technology and tools that we are using. Then in this case we start with somehow specifying the model itself. This is embedded into a model support package and uses it, and in a model foundation. So it means in our theory. That is again embedded in the modeling style and uses some model definitions. And in this case we say, okay, fine, we have now a class of models. I remember that we have had a stereotyping of modeling already in lecture 10. That means in this case you can say, okay, fine, I use for one class a specific, let's say, class definition, and use then styles according to the disciplines. I use then styles according to the mold. I'm using packages according to the situation. I'm using some kind of theory. I'm using some kind of tool support or some kind of technology support to handle it. It looks like a faraway dream. That's not true. We have already a very good example since the 70s. That is TeX or LaTeX. In TeX or LaTeX you start with developing your text, of course based on some kind of enabling technology in order to handle what you use as a text generation. You use some kind of foundations, you use some kind of packages, you use some kind of styles, you use defs, and of course you say, okay, fine, I'm using a specific document class. That means in this case it works already as a multi-level generation procedure. Starting with the inner generation for the model itself, for the content or for the text in LaTeX. Starting, of course, using some kind of technology and tooling support. And of course, inheriting whatever can be inherited by our model class. So we can embed our text directly in the model class and establish it by translation to a corresponding output text or document or program, so that we can handle it in a proper form. The same we can do for database modeling. In database modeling we do the same. We say, okay, fine, I'm using a model of my database structure. The model is maybe an entity relationship model or an advanced entity relationship model. Then I can say, okay, fine, I'm using some kind of environment. The environment could be, for instance, a tool that is called ArduXX, developed in Vienna University and used in a wide manner already for a number of modeling approaches. Then you can use a theory, you can use maybe some examples, some generalizations, some generic models, like for instance for the booking case, for the hotel booking case especially. You can say, okay, fine, my modeling style is globalist design. I use, because of the entity relationship model, some kind of object relational database management systems, and then I have a data structure specification. I think we should come back to it when we are talking about a compiler, how it can be established and how it is properly supported already nowadays. So, in this case, do we have some kind of supporting theories for the realization? It looks like it is impossible, but I claim that it is directly possible. We may use 3 success stories. One is Depot, what I already have been using it to explain how, let's say, specific domain-specific languages especially can be translated to general purpose languages in a proper form. We have been doing a similar experience with the rapid application and database development environment that allowed a specification of entity relationship structures and the translation to object relational structures. The same experience we have already with LaTeX as a very professional tool for support of publishing. That means in this case it is somehow useful. And we can base our technology on compilers, especially on 4-pass compilers that are a proper tool for supporting our approach. We are not lonely. There is a good number of trials. One is Genicore. You see here the Genicore display by a poster, and the claim modelware is the new software based on phenomena models. They can develop at least structure models, and they support like we do in database systems. Okay, let's now try to go to the compiler-compiler approach and to explain how the compiler-compiler approach is really working in a proper form. I think it needs a case study first of all. But a 4-pass compiler is nothing else as we say, okay, fine, we have some source text that is, of course, lexically analyzed. Then in this case we get a lot of information about the structure of the program. We have some syntactical analysis. The syntactical analysis results in a program tree so that it can be used for semantical analysis as a second pass after semantic analysis. Then we can use some kind of transformations to intermediate code. It optimizes intermediate code, and based on this optimization in the 4th pass generates the code, the target code in our other language. That is a classical structure of a 4-pass compiler. I was putting a very classical picture how it was done in the Depot system in the mid-70s already. It is based on some kind of model development framework that is in general layered. You start with the landscape. That means in this case with the application space, with the society and the community of practice governing the initialization. You go a step furthermore to the context and the discipline. Specialize this to the situation. Specialize this to the data, tracks and events you want to consider. And use at a certain level methodology and molds. The typical way is even that you say, okay, fine, I'm not selecting it, I'm reusing whatever has already been successfully used. And then you use the theories and the science, you use some tools, and finally you deliver a model within its functions in a given set of scenarios. That means in this case we have at the first landscape layer the problem space, the focus and the scope, mentalistic and codified concepts. We have some kind of identification, what is our interest, what kind of scenarios are somehow useful, what kind of model functions we want to have. In the intrinsic setup, you use a consideration of the background and of the concept world. You use the environment of stereotypes. You use some kind of origins world so that you can maybe base your consideration on maybe even generic models. That is, of course, our task of modeling. And you can use also some kind of configurations, embeddings. And finally, you start with using the origins to develop the normal models. That means based on settlement, adaptation, some kind of inverse modeling, as already explained, a very general approach, or some kind of conceptualization. And then you can come down with running and effective models that are assessed, that are evaluated, that are refinable, so that they will have some kind of proper support. Can it be done? Yes, is my claim. It can be done for object relational compilation based on advanced entity relationship modeling languages and the corresponding schemata, and based also, let's say, on something like programming environments like Visual SQL. And then you have a number of steps, maybe 13 steps in this case, how to develop a database application based on the model. That means you can now go through all these steps, what we have been doing already in the entity relationship book in the 90s last century. Okay, can it be done on a rule-based in a rule-based form, so that we can use rules to generalize to specify our, let's say, compilation? That would be nice. Let's consider a case. Let's say we develop something like booking.com applications, booking a hotel by, let's say, an agent or a guest, and in this case you would like to have some kind of, let's say, support. We can concentrate on some of the issues that let's say you book a hotel as a guest or as an agent, of course, in a hotel chain, and in this case you book some kind of room type, not really the room itself. And of course you are interested in how much it costs. That means in this case you need to have an information that the room has, let's say, a certain rate for paying. Okay, fine. That would be the first step. Then you can say, okay, fine. What I need now to do is I need to prepare for translation. In this case, I need to know what are the specific views I would like to support. For instance, if we have a staff member that is somehow handling our booking, then in this case I have a view of the staff member of a certain hotel in a certain hotel chain for, let's say, the booking of a guest or an agent. That means in this case I have a number of views to support those. That means in this case I develop my views. Then in this case I can also add to my model a number of directives. Model directives are the treatment of hierarchies, which kind of redundancy I would like to have, the null marker support, constraints treatment, naming conventions, etc. And then you can say, okay, fine, I'm using a number of realization styles and tactics. Remember what we have learned about the latte case. I'm adding configuration parameters for the coding, for services, policies, handlers, and anything else. I'm using generic operations like we do in database in any case for our insert, delete, and update operations. I'm adding hints for the realization of the database, for performance expectations especially. I add some kind of constraint enforcement policies. I add also supporting features for system realization. And maybe since the structure I have been developing is not the structure that is most effectively supported in a database management system, I add something for normalization and pivotization. And finally, I might add something like a quantity matrix or Mengengerüst for all types, including entity types. In this case, you say, okay, fine, I have now a number of model directives. And I add for my compiler, as we do in sophisticated compiler technology, pragmas for the rule-based transformation. That means I have realization styles and tactics. I have configuration parameters. I'm basing my support for functionality of database applications on generic operations. I add my hints, I have performance expectations, my constraint enforcement policies, etc. Whatever you can add. So in this case, my specific case of, let's say, a model or a hotel booking is nothing else. It is saying, fine, I would like to have a booking for a room in a hotel at a certain location in a certain hotel chain, maybe based on some additional information, so that I can characterize by so. Then in this case, you say, okay, fine, it's nothing else as taking this structure and translating it to proper SQL based on rules. I should show the rules in a minute. Then in this case, you can say, okay, fine, it is not only a simpler structure, but it can become pretty large. But I think this left side is far simpler to handle than the whole stuff what you can directly translate with a given structure in our entity relationship model. Then you can say, fine. Then you have also rules. For instance, if you have a cluster type, for instance, we have here had a cluster type that you say, okay, fine, a booking can be made either by an agent or by a guest. Okay, if you have such kind of cluster types, you need a rule to handle it in a proper form. And the rule could be that, okay, fine, I have a number of, let's say, interpretations of the cluster. If nothing is known, okay, then I use one option. If I would like to use a combination form of the translation, I'm using the combination form, or the separation form, or the surrogate form, or the view, or the union form. That means these are 4 different translation facilities I can use for the translation of a cluster. And in this case, I say, okay, fine, my rule looks in this case like an if-then-else rule. I can have some kind of representation for it. And in this case, I can say, fine, now I can translate whatever has been given in my database application. And then in this case, you can translate it, let's say, to classical relational structures. You say, okay, fine, you have a booking agent. In the separation of for the cluster, you have a booking guest. So this is separation now, and then you can say, okay, fine, somebody can book, and you have, of course, some kind of relationships between the guest who is booking and the agent that is booking. So in this case, you have a number of constraints. And of course, you can say either an agent is booking or a guest is booking. And of course, you can also say a booking date is nothing else as some kind of timestamp. The same can be done for the continuation of the whole booking. That means in this case you have structures plus syntactic constraints handling all these things. In this case you can say, okay, fine, you have also a booking guest handled in a proper form. And you might now look what to add to the schema. First of all, you should add to the schema some adornment to the complex attribute types in order to know how to translate a complex attribute type to the very basic attribute type we have in object relational database systems. So in this case, you say, okay, fine, I have a number of adornment stating what I want. For instance, I want to have flattening or mapping or separate representation in an unnesting or in a better form. So in this case, you can say, fine, I have also an adornment for the relationship types translation, because it is not a unique translation, it is a translation with several opportunities. And in this case, you can say, okay, fine, I have these and that transformation facilities. In the same form, you can also trade hierarchies. There are essentially 4 different approaches: even non-separation approach, even separation approach, bulk approach, and the generalization and specialization approach. The union approach is a little bit, let's say, problematic. For this reason we avoid such approaches. That means in this case again you have a treatment of hierarchies. You have a number of integrity enforcement tactics you can directly specify with a given set of integrity constraints. You have a number of transformation of integrity constraints. You have a number of default options you can use in this case and handle it somehow in a proper form. That means in this case you can say, okay, fine, I'm accepting these default options, and for this reason I don't think about adornment, I simply use it somehow. And then you can use some kind of pre-processing of the conceptual database schema. That means in this case I'm preparing now, as we did in semantical and lexical analysis in the compiler, as a pre-processing of the conceptual database structure. Okay, you have in this case to use, of course, some kind of transformation directives. Directives that can be used later for handling or for mapping the compiler translation in a proper form. Directives are directly also translated to compiler pragmas, and for this reason you can use them in this form. Then you have again, then you have this kind of rule-based compilation, and you can translate it somehow. Then in this case you can also say, okay, fine, I want to have a special transformation style. For instance, I want to have it in the classical salami slice approach. That means an entity type is as much as only possible a harmonic type. That means a harmonious type. So in this case, all objects in classes of that type have the same structure. You can do it also with, let's say, the Russian dual tactics we use typically for XML documents, or you can use the approach to a Venetian vase. That means in this case you say, okay, fine, a number of components can be somehow compiled together. That means in this case we have now a little addition to what has been done. Donald Knuth has been proposing an approach to literate programs. We would like to extend this approach now to literate modeling. Generalize it in such a way that this can be supporting our development of database structures together with the development of proper viewpoint support. So that means in this case I say, fine, my viewpoints are somehow represented by views on my given database schema. That means in this case we have something like literate modeling already. Okay, let's start with the second proof of concept. So far we have been considering the global as design approach. We can also consider the local as design approach. And let's say in the second case study we could do it for storyboarding. Storyboards and site length specifications are mapped to BPMN specifications. Both are using different paradigms of representation. For this reason we should use these different representations in a proper form. Let's say, for instance, I would like to have something like planning a trip, supported by a website, of course supported by an BPMN execution machine. Then in this case I say, okay, fine, I have my storyboard, I go look for the map, I browse, select something, I develop my planning for the trip, and it is of course free of, let's say, movement from ever place I can go there. Of course BPMN is far more restrictive. It says you have to have a certain way and only a certain choice that is implemented. So it means in this case we should now know how to calm down, how to generate a proper BPMN set or diagram set, so that we can use it as a representation of the storyboard, saying that not all options are somehow given in the BPMN diagrams or supported by those diagrams, but at least the main of them are supported. That means in this case we have now different sort styles. You have our mindsets are completely mismatching. We have different paradigms, different postulates, different assumptions. We should now demonstrate that this is still translatable. So that means in this case a compiler could exist. And how we can do it now? Okay, we start first with somehow stating what is a representation. An actor storyline is represented by a pool. That might be a little bit too restrictive, but let's say we do it. So in this way we have a very specific interpretation of our actor storyline. The same can be done for an actor scene. The same can be done for a story sequence. The same can be also done for, let's say, the opportunities and the mappings we have in our storyboard. That means in this case we have a number of rules again, how to translate a certain side length specific element to a BPMN element. And then we might be able to translate it. Okay, in this case we have now to add a number of tricks. First of all, we would like to have BPMN diagrams. That means in this case we should represent as harmonic as possible passes through our story space. In this case we use an approach that has been successfully used for web information systems already. We separate our storyboard into mini stories, and the mini stories later will become BPMN workflows. We use some kind of refinement pre-processing. We restrict, of course, the freedom now. Not anything is supported, but only the most essential, let's say, passes in our story space. We restrict and use some kind of well-formed parallelism. We restrict ourselves also to some kind of normalization, to some plot integration, to some graph grammar rules. So in this case we can say, okay, fine, now my general storyboard can be now somehow translated to a BPMN diagram for a visitor. The visitor has to select a certain location from a map. Then, of course, the visitor can go either by issue a report or by trip planning and navigating along. That means in this case our freedom of movement is not anymore supported. In this case we can say, okay, fine, a visitor trip planning would now be supported by such kind of BPMN diagram. It looks pretty simple. It is, however, restrictive. We have, let's say, some kind of selection. From the selection point we can go now, let's say, to an issue report. With the issue report we can directly conclude the issue report, or we can somehow use, let's say, the join to go, let's say, to a trip selection, a negotiation, and we can again come back here through this cycle. That means in this case we have now restricted our opportunity space of moving through the storyboard to a very specific interpretation. To make a claim or to have an issue report is only possible after I have been using an explicit path towards it, or I have been using some kind of selection of the trip, and then I can issue some report. That means we have now in the BPMN diagram less freedom. Okay, I should come down now to the end of this lecture. We have been using for our realization some kind of layered approach, starting with the landscape, going with the intrinsic to the extrinsic to the tool supported part for generation. Okay, that is a path towards modeling as programs, or modeling to program. I would not say that this is a silver bullet. It is one of the possible instruments. It is an engineering approach. There's a very famous nice saying by Theodor von Karman: scientists look at things that are and ask why. Engineers dream of things that never were and ask why not. That is a very nice specification of the difference between a scientist and an engineer, and science and engineering. Ure said engineers use materials whose properties they do not properly understand to form them into shapes whose geometries they cannot really properly analyze, to resist forces they cannot properly assess, in such a way that the public at large has no reason to suspect the extent of their ignorance. I think this is very nicely characterizing our engineering approach to modeling as programming, with an intermediate step of modeling to programming. The next lecture will be now on quality issues of a model. The model should be dependable. That means it should be of an appropriate quality, and for this reason we need, of course, also quality characteristics we can use, and we need to have some kind of quality assessment procedure. I would like to introduce, in this case, a number of quality pattern for specifying whether the goal, purpose and function of a model is really proper. We call it poor, smart and clear. Or for evaluation whether, let's say, the internal and the external and the quality of use is really proper, we should call it step. Or whether the model development was really proper, I call it now quartz sand, where I should specify what the letters in poor, smart, clear, step, quartz sand means. And finally, I should be able to specify the potential and capacity of a model in a SWOT or scope, let's say, stereotype of model assessment. That is now the next lecture coming with the next steps. Thank you for the attention. So in this case we have now to go for real consideration what we have been doing. That means to fit the cat into the box. Thank you for the attention. Next lecture will be now on the quality of models.